Okay, so in this video I'm going to go through the answers to the exam questions at the end of 17.2, which is on infrared and on mass spec. So the first one, you're given an infrared spectrum and you're asked which of the molecules could have produced this spectrum. So I know there's lots going on here below 1500, but below 1500 is what we call the fingerprint region. It's hard to analyze, and we tend to just ignore everything below 1500. So I'm just going to focus on the peaks on the left hand side of the spectrum. The first clear peak I've got here is around at 2200, and if you use your tables, you'll see the only thing that around 2200 is a nitrile group, which is a C triple bond N. So I've labelled that there as a nitrile group. Now I know I said you'll typically be tested on the alcohols, the carboxylic acids and the carbonyl groups, but you are provided with the full table, and you can be asked to identify any functional group. The next one I've labelled here is at around 3500. And again, if I look at my tables, the only thing up this high, 3500, is either an NH for an amine or an OH from an alcohol. There is another little peak here, okay, just at around 3000, slightly less than 3000. This peak here would be from just CH. So you'll find that in all organic compounds, so that can often be a little bit confusing because it can overlap with a carboxylic acid, but in this case it would just be a CH. So if I look at what I've got, I know I need to have a nitrile group, so the only molecule here with a nitrile group would be B, the CN, and then as well I've got an OH from an alcohol, and B also has that OH there from the alcohol, so it's written backwards as HO, but it is the OH from the alcohol. D might have potentially been a possibility for this peak here, the NH peak, but it also has a CO, a carbonyl peak, which is not present in our spectrum. So I know that the answer is going to be B. Okay, in the next question, you are told that you heat an alcohol under reflux with sulfuric acid and potassium dichromate. So you would need to recognize those reagents as oxidizing reagents. And if you're oxidizing an alcohol under reflux, you've got two possible products. You can either make a carboxylic acid if it's a primary alcohol, or a ketone if it's a secondary alcohol. So whatever your oxidized product is, it has given you this infrared spectrum. So if I analyze the spectrum, I should be able to see if it's a ketone or a carboxylic acid. So I have my peak here at around about 1700 to represent my carbonyl group. Okay, that will be present in the carboxylic acid and in the ketone, so it doesn't tell me much. But then I come up here and I see that I don't have the OH from the carboxylic acid. So if you had a carboxylic acid, you would get a broad peak between 2500 and 3300, and we do not have that broad peak from 2200 to 3300. The peak that is there is just from the CH bonds that you get in every organic molecule. So if I've got the carbonyl group but I don't have the OH, then it must mean it's a ketone, not a carboxylic acid. And if this is, so you're asked about the alcohol, if this is the oxidized product, it's a ketone, then you must have started with a secondary alcohol. So if you look at the alcohols that they give you, okay, the first alcohol they give you is tertiary. So remember, you're looking at the carbon that the OH is bonded to, and this carbon is bonded to 1, 2, 3 other carbons, therefore it's tertiary. In B, there's your carbon, and this carbon is bonded to 1, 2, so that's secondary. So at the moment I'm leaning towards B as my answer. Then I've got C, this is the carbon I'm focused on, and it's bonded to just one other carbon, so it's primary. And then down here, this is the carbon the OH is bonded to just one other carbon, so it's also primary. And that must mean that your alcohol is B, a secondary alcohol, because your product after oxidation is a ketone. So 3 and 4, you can get the answers straight from the mark scheme. There's nothing difficult there, just pay attention to what's required. For part 2 though, they ask you to suggest the molecular formula of 2 ions responsible for peaks from C that you don't get in F. So all I did here was I just cut C in half, and I had a look at what I ended up with, and if I break it in half, I get one fragment, CCl3. There is no possibility of having a carbon bonded to 3 chlorines because that doesn't exist in F. And the other carbon is bonded to 2 fluorines and a chlorine. And again, over here, you'll see that neither of your carbons are bonded to 2 fluorines and a chlorine. So they are your 2 fragments. In order to get the full 2 marks, though, you need to have a positive charge on both of those fragments. Okay, you'll lose a mark if you don't include your positive charge. Only ions produce peaks. The next one here is actually from a previous topics from chapter 15. You're asked for the mechanism to show the hydrolysis of a haloalkane. So when you are using aqueous sodium hydroxide, your actual, we all know, well hopefully know that sodium hydroxide is NaOH, but the actual reagent you're using then is the OH minus. That's all I need to show in my mechanism. I don't need to show the sodium at all. So I've drawn out my haloalkane, okay, and you need to include the dipoles on your carbon-halogen bond. So the carbon is delta positive, the halogen is delta negative. It's, as I said, the OH, the hydroxide ion that I need to show as my nucleophile. I need to start my curly arrow on the oxygen. So I can either start it on the lone pair on the oxygen or the negative charge. Actually, I really like my arrow. I'm going to change that slightly. I need to start it either on the lone pair or on the negative charge. I'm going to start it there from the negative charge, and it needs to go to my carbon. Then this bond is going to break, and then this is going to be a product. So it's a substitution. So if you read the mark scheme, it says that this was answered very poorly, and the main reason it was answered so poorly is because the arrows weren't specifically about the OH minus. So if you drew something that looks like this, so if you wrote OH minus and you started the arrow on the negative charge, that would be wrong, okay? And even though you're starting the arrow on negative charge, that negative charge is not on the oxygen, so it looks like the hydrogen is attacking the carbon, and that's not the case, okay? So you can either draw it, you can write it as OH minus with the hydrogen next to the negative charge, but if you do that, then you need to include the lone pair on the oxygen, and you need to start the arrow from the lone pair. So the arrow has to start from the oxygen, and it has to specifically start from either the lone pair or the negative charge. You don't need to include the lone pair if you put the negative charge on the oxygen. That would be totally fine. Okay. The other common mistake was not showing that the Br minus. So what students did is they wrote NaBr, so sodium bromide, as the product. If you don't show that the bromine ends up with a negative charge and it forms a bromide ion, you don't get that last mark. So again, if you look at the mark scheme, it says that it would accept NaBr as long as you showed the charge on the bromide ion. But if you just wrote NaBr, you weren't going to get that mark. So my advice on this would be to just leave out the sodium altogether. Just use the OH minus as the nucleophile and just show the Br minus at the end. The second part of the question then is back to what we were talking about, and we have got the infrared spectrum, and it asks you how you use spectroscopy to show that the bromoalkane functional group has reacted. So you're going from your bromoalkane to your alcohol. So they've labelled this CBr peak here for you because, as I said, we are never asked to interpret anything below 1500. So they've labelled that for you. And what you'd expect to see on the infrared spectrum of your product is that CBr peak would disappear. It wouldn't be there anymore. The other difference you're going to see is you're now going to form an alcohol. So if you're forming an alcohol, you are going to have a peak between 3200 and 3600. So to get the 2 marks, you have to say the carbon-bromine peak disappears on the alcohol, and you have to say that you get the new alcohol peak formed. And you can use the table in order to get the relevant wave numbers. So the next one here, they give you a couple of different molecules, and they ask you to carry out some analysis to find out which one it is. So they give you your percentage composition by mass. They ask you to calculate empirical formulas. This should be something we are all able to do. You just divide the percentages by the atomic mass. So for carbon, the atomic mass is 12, hydrogen, the atomic mass is 1, oxygen, the atomic mass is 16. So I divide across. I end up with this as a ratio. I then simplify my ratio by dividing by the smallest number. So 0.658 is the smallest of my 3 numbers. I divide everything by 0.658 and I get a whole number ratio of 10 to 16 to 1. So my molecular formula there, my empirical formula there is C10H16O. They then also give you your infrared, and they ask you to analyze this. So again, we're going to ignore anything below 1500, which means we're only focused up here. And this is a bit of an awkward one to interpret, okay? So you do have something all the way up here at 3500. As I said before, the only thing you have up this high is the NH and the OH. We've already seen for our empirical formula that we don't have any nitrogens. So to have a peak up this high, you must have an OH coming from an alcohol, not coming from a carboxylic acid, coming specifically from an alcohol to give you a peak up that high. There is also something there that you can see at 3. So again, if we're looking at my empirical formula, I know I've only got one oxygen, and I know I've got the alcohol group, so there's unlikely that this peak here is anything noticeable. And again, if you look, that other peak there at 3000 can just be your CH, from which you're always going to have present. So I've got the OH from an alcohol, and then this is just a CH peak. And I get that you might be like, it's very broad. Maybe it's this OH of a carboxylic acid, okay? But if you look at your molecular formula, you see you've only got one oxygen. You know you've got an OH. There's not going to be a carboxylic acid there. So I know I've got an alcohol group. So if I go back up and look at the molecules, I see A has an alcohol group, and I see C has an alcohol group, and the other 3 do not. So I know it must be A or C. And then I look at my molecular formula, C10H16O, and a quick count will reveal that C is the correct answer because it's got 10 carbons, 16 hydrogens, and 1 oxygen. If you quickly 1, 2, 3, 4, 5, 6, 7, 8, you'll see that A only has 8 carbons and it cannot be correct. So you label your spectrum, okay? You get marks from just labeling the spectrum, but then I would also write it out underneath the process I've just gone through, so you can just check the mark scheme to see how to word it. The next one, again, they're giving you an alcohol and they're telling you it's a branched chain, and they tell you heat it under reflux, again, with H2SO4 and potassium dichromate. So again, they're not using the word oxidized. You need to recognize that this is your oxidizing agent. If you're oxidizing an alcohol under reflux, again, your 2 possibilities are a carboxylic acid or a ketone. So again, this is the spectrum that shows the oxidized product. So if I have a look, I see a clear peak here at around 1800. That's your C double bond O. Again, that will be present in a ketone or a carboxylic acid, so it doesn't tell you much. But if you go over here, you don't have the OH from the carboxylic acid. So if I were to have the OH from a carboxylic acid, I'd have a really broad peak between 2500 to 3300. I'll just remind you what that peak would look like, okay? So this is what you would be expecting, and if we look at what we've actually got, you don't have that broad peak. So I know I don't have a carboxylic acid, which must mean my oxidized product is a ketone, okay? So I've written that here below, okay, so I've done my analysis. So when in order to get the marks for your infrared, you need to write the wave number of your peak. So I just took this directly from the table, or else you can be more specific and read it off the spectrum that you're given. So I'm identifying that that peak is a C double bond O. You can label it on your spectrum as well. And then I'm also saying that there's no peak between these wave numbers, so I don't have a carboxylic acid. If I know that I'm forming a ketone as my oxidized product, then I know that J, my alcohol, must have been a secondary alcohol, because you oxidize a secondary alcohol to form a ketone. So I know that J is a secondary alcohol, okay? It then wants you to determine the structure of J, okay? So they do tell you that the molecular formula is C5H12O, okay? So I know it's C5, I know my molecular formula is C5H12O. I know it's a secondary alcohol, and the other piece of information that they give me is they tell me that it's branched, okay? So I need to use that information, just that information, to put together a structure, a potential structure for this alcohol, okay? So C5, and I know it's branched, so instead of drawing all 5 carbons in a row, I'm just going to draw 4 carbons in a row, and then I'm going to create a branch, okay? So it doesn't matter whether I put my branch on carbon 2, or if I put it there on carbon 3, okay, but obviously I can't put it on the end, or else I'd have 5 carbons in a row, all right? I know I have to have a secondary alcohol, so I'm going to draw this bit nature, it's a mess. I know I have to have a secondary alcohol, which is going to limit where I can put my OH, okay? If I were to put my OH on either end, I would have a primary alcohol, and then that wouldn't give me a ketone when I oxidize it. It would give me a carboxylic acid. So therefore, I'm going to be putting my OH here on this carbon in order to give me my secondary alcohol. Now you might have said, well, what about putting it on the same carbon as your branch? Okay, but if I do that, then I have, remember, to see if it's primary, secondary, or tertiary, you're looking at the carbon the OH is bonded to, and this carbon is bonded to 1, 2, 3. So if I put the OH and the branch on the same carbon, I'm creating a tertiary alcohol, which cannot be oxidized, okay? The way I've done it here, I've got my secondary alcohol, and I've got my branch chain. You might also ask, well, how did you know that there was 4 carbons in the chain? I could draw 3 carbons in the chain and have 2 branches, and I'm still getting all 5 carbons in there, and it's still branched, and that is correct. But when it comes to putting my OH in, okay, there's nowhere for my OH to go that gives me a secondary alcohol, okay? If I were to put my OH here, this carbon will be primary. If I were to put my OH down here, it would be a tertiary alcohol. Okay, so there's nowhere to put that OH that gives you a secondary alcohol, which means this here is your only possible option. And you can do that by a little bit of trial and error. The last thing asks you to write an equation of the reaction of J, so J is your alcohol, when you heat that under reflux to form K, and you're using just O in brackets to represent your oxidizing agent. So when you're asked to write an equation, unless it specifies, you can use any type of formula you like, and I love skeletal, so I always use skeletal unless I'm told otherwise. So there's my secondary alcohol. I'm reacting it with my oxidizing agent, which I just use in square brackets. I'm going to form a ketone. There's my ketone K. And the other product I form in an oxidation reaction is water. And that is already balanced, 2 oxygens on the left, 2 oxygens on the right. The next question, again, a bit of an aside, they just ask you about solubility. So I drew out my alcohol again. I just kind of flipped it around a little bit so that the OH was facing the other way. But I drew out my alcohol and I drew a molecule of H2O. In order to get the marks for this, you need to show the delta positive and the delta negative, okay, on both, on your alcohol and on your water molecule. You don't need to put the other delta positive there, but you need to have the dipole shown on both. And then, and this is the bit that apparently most people lost marks on according to the examiner's comments, is you need to show the lone pair on your oxygen and then label that hydrogen bond. Okay, so what the examiner said most people did was just forget to put the lone pair on the oxygen. Now I've drawn it from the oxygen of the alcohol to the hydrogen of the water. You equally could have drawn it from the hydrogen of the alcohol going to the oxygen of the water. As long as you're going from a delta positive hydrogen to an oxygen lone pair, you'll get your mark, okay? But just make sure you're completing your dipole. If I got rid of my delta negative, if I got rid of my, even though this hydrogen isn't part of the hydrogen bond that I've drawn, I still need to show it's delta positive. And similarly here, even though the oxygen isn't part of the hydrogen bond that I've drawn, I still need to show it's delta negative. So this next one, actually, I mean, this is quite tricky. This is probably the hardest of the questions, okay? So, but there's still, even though the last bit might be difficult, there still should be plenty of marks that you can get, even if you don't get all of them. So the first bit that we've got here is just finding out the empirical formula. So again, you're going to divide those percentages by your atomic mass. So 12 for carbon, 1 for hydrogen, 16 for oxygen. You then simplify the ratios to get whole numbers, and you end up with C4H8O3. Okay, so you're starting off with compound A, you're reacting it with kind of humid air, and you're ending up with this new compound with the formula C4H8O3. They have the infrared spec for that new compound, so we're going to analyse it below. Okay, again, I'm ignoring everything below 1500. The first peak I'm focusing on here is around 1700, and as we've seen a number of times before, that's representative of a carbonyl group. Now, that carbonyl group could be part of an aldehyde, a ketone, a carboxylic acid, so we always need to look a little bit further. Okay. I do think this is quite a difficult one to interpret, okay? So you do have the OH from a carboxylic acid, okay? You've got this broad peak here. This is a broad peak. I know it gets narrower at the bottom, but it is a broad peak, and it's coming there just below 3000, okay? So if we look here at carboxylic acids, that peak is exactly in range between 2,500 and 3,300, and we do have that there kind of starting at 2,500 and going up to 3,000. We've got that broad peak, and that's the OH from a carboxylic acid. We've also got another peak up even higher, almost at 3,500. And again, you'll see the only peaks up that high are the NH and the OH. Looking at our empirical formula, there is no nitrogen, so that peak must belong to the OH of an alcohol. Okay, so I've got my C double bond O, that must be part of my carboxylic acid group. So I've got the OH and C double bond O, so I know I've got a carboxylic acid group. I also know I have an alcohol group, and they are going to be separate from each other. Okay, so we then need to come up with a structure for compound C. For compound C, all right? So I'm going to start off here for compound C. It's got 4 carbons in total, all right? So I'm going to draw those 4 carbons in exactly the same place that they were before, okay? I'm going to fill in my hydrogens on both of the CH3s. I'm not going to draw in the chlorines because I can see from my empirical formula that those chlorines are no longer there. Okay, so I've drawn pretty much the same thing, except I've left off the chlorines and I've left off the chlorines. Okay, and I know instead of putting those chlorines in, I'm just going to make this a little bit neater. Instead of putting those chlorines in, I now need to get an alcohol group in there, and I need to get a carboxylic acid group in there onto those remaining 2 carbons. Now, I need to decide which way around I'm going to do it. All right, a carboxylic acid group has got a double bond O and a single bond to the OH. If I look at this top carbon here, just because of its position, I can't put a double bond O and a single bond OH. I can't make that carbon a carboxylic acid because there's only space for one more bond. However, the carbon here below, I do have the space to make that a carboxylic acid. I can go double bond O, single bond OH, and I've got my carboxylic acid group in. That leaves this carbon here to take on the alcohol group. And if I do a quick check, C4, I've still got 4 carbons. H8, I've got 3, 4, 7, 8, and 3 oxygens. I've got my 1, 2, 3 oxygens. Okay. I've also got the carbonyl group and the OH for my carboxylic acid, so that's how I knew there was a carboxylic acid. And I've got the OH for my alcohol, so I knew there was an alcohol. I'm losing those chlorines because I can see from my empirical formula that those chlorines are no longer there. That is quite a tricky question, though, I think. And then the last of the questions, okay, again, you are given some information about a compound. Again, I'm told that it's a branch, that's going to be important, and I'm told it doesn't have E or Z isomers. So as soon as I see those E and Z isomers, I'm thinking this is likely going to end up being an alkene, because why would they be talking about E and Z if it wasn't going to be an alkene? They give me, again, the elemental analysis, so I haven't worked this out, but it's all in the mark scheme, okay? Again, you're using these percentage compositions to work out the empirical formula, and you should get C4H6O2. They then provide you with the mass spectrum and the infrared spectrum, okay? So, personally, I would find the infrared, I would find the infrared spectrum a bit easier to start with. Okay, but if you want to start with the mass spectrum, what I did initially was just label. So here my molecular ion peak is 86. Okay, so I'd label that as 86, and then the 2 fragments that they want you to analyse, one has a mass of 41 and one has a mass of 45. I then came down and had a look at my infrared spectrum, and again I'm seeing that peak there at around 1700. That's going to be my C double bond O, but again that could be part of an aldehyde or a ketone or a carboxylic acid, okay? And then if I go up a little bit further, I know this peak isn't dipping down quite as much, but you do have a broad peak between 2500 and 3000, so that's going to be your OH from your carboxylic acid. So you'll see that these peaks can look a little bit different on different spectrum, okay? But as long as it's within the range and it's clear peak, you know, this, if it was all the way up there, there'd be nothing, but it is a clear peak in that range. So that's the OH from the carboxylic acid. So the fact that I've got a carbonyl group and I've got this OH from the carboxylic acid, that tells me I must have a carboxylic acid functional group, and that fits with my formula. I've got 2 oxygens, which is consistent with the carboxylic acid. So if I've written some of this out, okay, so it asks you in the question to calculate the empirical and the molecular formula. So by doing the percentage composition data, this is the empirical formula, but then you have to show that the empirical formula and the molecular formula are the same, and you'll do that by using the data from the mass spectrum. Okay, so I have to find the formula mass of my empirical formula. I see that that's 86. I read that the molecular ion has a mass of 86 from my mass spectrum. Because the formula mass of the empirical formula and the molecular mass are the same, then that tells me that the empirical formula and the molecular formula are the same. So that's me calculating my molecular formula. Then you have to write the formula of the particles responsible for peak X and peak Y. So at this point, I've just written down the mass charge ratio for X and Y. And then I said I moved on to the infrared, and I figured out that I had a carboxylic acid group, because as soon as I found out I had a carboxylic acid group, I found it a lot easier to go back and do the mass spectrum. So it's fine to do it in a slightly different order. Okay, if I know I've got a carboxylic acid group, okay, if you look at just the carboxylic acid group by itself, you've got a carbon, you've got 2 oxygens, you've got 1 hydrogen. Add that all together and you've got a mass of 45. So this peak here, Y, which is 45, is just going to be the carboxylic acid group itself. And you're remembering to put that positive charge on that ion. So that's just going to be your carboxylic acid group. Okay. Also, if you look at the total formula mass is 86. So if this fragment is 45, then the other fragment, 41, is just the other half of the molecule. So once I've figured out that this part is the COOH, I just need to remove the COOH from my molecular formula, and what I'm left with will have a mass of 41. So I've used 1 carbon, which means I've got 3 carbons left. So it's C3. I've removed 1 hydrogen, so I've got 5 hydrogens left. And I have removed both of the oxygens, so I've got no oxygens in my other fragments. And again, I'm putting a positive charge on that, okay? Because the 2 peaks taken together add up to 86. If 45 uses carbon, 2 oxygens, and hydrogen from my carboxylic acid group, then the 41 peak has the remaining atoms, okay? But now I need to put all of this together and actually draw a structure of compound G, okay? So I know it's got 4 carbons, and I know that it is branched. So because I know it's branched, I'm going to draw 1, 2, 3 in a row, and then I'm going to draw a branch, okay, which is going to have to come off the middle carbon, so I'm going to draw a branch, okay. I know I've got a carboxylic acid group, so it doesn't matter where I put the carboxylic acid group, it can't go on this middle carbon here, but the other 3 carbons it will fit, and they're all equivalent, so I'm going to put my carboxylic acid group there. Okay, so I've drawn my 4 carbons, I've drawn my 2 oxygens, I've currently only drawn 1 hydrogen, I've got another 5 hydrogens to go. So I've only got another 5 hydrogens to account for. If I was just to put hydrogens in the remaining spaces, I'd have 3 hydrogens there, 3 hydrogens there, and 1 there. So I need another 7 hydrogens, yet my molecular formula tells me I've only got 5 left. And then I think back to the clue here at the top about the EZ isomers. Okay, that was suggesting that it was an alkene, which means there must be a double bond someplace. Okay, so I can't put a double bond between these 2 carbons because this carbon would have too many. It's already got 4, so there's no space for a double bond. Okay, both of these carbons are equivalent, so it doesn't matter where I put my double bond. Okay, I'm going to put my double bond here. All right, that's not very clear. So I'm going to put my double bond between those 2 carbons. And now I'm going to fill in my remaining hydrogens. I can fit 3 hydrogens there. And now I can only fit 2 hydrogens there. So that gives me 4 carbons in total, it gives me 6 hydrogens in total, and it gives me 2 oxygens in total, which matches my molecular formula. It gives me my carboxylic acid group, which is consistent with my infrared data. It gives me a branch, which is consistent with what I was told at the start. I've got an alkene, and then if I look, it doesn't have an E or Z isomer. So to have an E or Z isomer, each carbon of the double bond must have 2 different groups. This carbon has bonded to 2 hydrogens, therefore it will not have E or Z stereoisomers. So what I've drawn is consistent with all of the data. The other thing just to point out is it is consistent with your mass spec. If I were to break the molecule right here, then this portion here would have a mass of 45, and the remaining portion here would have a mass of 41. So then you could go back to your mass spec analysis and just draw this as the C3H5 once you've got it figured out, in case that was required, although the mark scheme does accept just the molecular formula by itself as long as you've got your positive charges.